Hi, Mr. Richards here. Today, 7th grade, Unit 4, Lesson 6, Anchor Problems, our second day of looking at word problems with equations. Julia, Keller, and Israel are volunteer firefighters. On Saturday, the volunteer fire department held its annual coin drop fundraiser at a streetlight. After 1 hour, Keller had collected $42.50 more than Julia, and Israel had collected $15 less than Keller. The three firefighters collected $125.95 in total. How much did each person collect? Well, let's draw some pictures to help us visualize what's going on here. All right. We have Keller with 42.50 more than Julia and Israel with 15 less than Keller. So let's start with Julia. Like, why start with Julia? Trust me for a second here. Let's start with Julia. Do we know what Julia has? No, not really. But if I draw this bar here, or a tape diagram is another way of calling it, that's how much Julia raised. Right here, right there. That's Julia. All right. What about Keller? Well, we know Keller collected $42.50 more than Julia. Well, how can I visualize that? Well, Keller did what Julia did, plus an additional $42.50. So I can tack that on right there. So we have Julia. Keller was Julia plus 42.50. Well, what about Israel? Well, we know Israel is 15 less than Keller. Well, 15 less than Keller, I have 42.50 here for Keller. So if I subtract 15 from that, I end up with $27.50. And so what Israel really is the same as Julia, but instead of being plus $42.50, he is only plus $27.50, which is $15 less than Keller. All right, so now you may be wondering, okay, that's fine and all, but how do I get to what I'm looking for? What if we call Julia X? Keller would then be X plus the 42.50, and Israel would be X plus the 27.50. And so I could set up an equation. to solve this. I would have X plus 42.50. So we have Julia's plus Keller's plus Israel's X plus 27.50. Oh, but wait, what is that all equaling? Well, didn't they all together raise $125.95? So this equation equals $125.95. And so I can look at these like terms here, these x's. I can go, okay, let's take the x plus the x plus the x and call that now 3x. Then I could take this 42.50 and add it to the 27.50 and get, well, 70. And that's going to equal $125.95. And now I have a two-step equation to solve. If I subtract 70 from both sides of the equation here, we end up with 3x is equal to $55.95. And once I divide by 3 on both sides of this equation here, because the opposite of multiplication is division, we end up with x equals $18.65. All right, we're not done yet, though. We need to go back and find out what this all means. Well, we know Julia was x. And if X is $18.65, Julia is simply $18.65. What about Keller? We know Keller was Julia's $18.65 plus $42.50. When we add those together, we get $61.15. And for Israel, a couple ways of going about his. But I'm going to take this $18.65 and you can add $27.50, or you could take Keller's at $61.15, right, and subtract 15. That's another way of getting there. But either way you were to take, you get $46.15. If you added those all up, you would get the $125.95 that they raised. Continuing on to problem 2. Your parents are redecorating the dining room and want to place 2 rectangular pictures, each measuring 25 inches across, on the wall, which measures 10 2/3 feet long. They want to place the pictures so that the distance between the pictures and the distances from each picture to the end of the wall are the same, as shown in the diagram below. Well, you have the 10 2/3 feet, you have a distance, you have the 25 inches, a distance, 25 inches, and the distance, and these distances are all the same. So our question asks us, determine the distance each picture should be placed from the ends of the wall and explain the strategy that you used. Well, let's work in inches here, okay? We know that 12 inches equals 1 foot. And we do need to notice in this picture now that this 10 2/3 feet versus 25 inches. I think it's going to be easier to work in inches here. All right, so let's figure out 10 2/3 feet equals how many inches? Well, if we separate this out, the 10 feet times 12 inches per foot is equal to 120 inches. The 2/3 feet times 12 inches per foot is equal to 8 inches. So this 10 2/3 feet is actually equal to 120 plus 8, which is 128 inches. So this whole distance is 128 inches. We have this distance and the 25, this distance and the 25, and this distance being equal to the 128 inches. So we could set up an equation. Yes, an equation. If we call this distance x, and this distance x, it looks like I have 1, 2, 3 x's plus this distance and this distance, which is 25 plus 25, which is 50 inches. And that equals this entire 128 inches across. Let's solve that equation. If we subtract 50 from both sides, we're left with 3x is equal to 78. Then, opposite of multiplication is division. So if we divide by 3 on both sides, we end up with x equals 26 inches. So each of those distances there is equal to 26 inches. And sure enough, if you were to add up 26 plus 25, 26 plus 25 plus 26, you would get that 128 inches, which was equivalent to the 10 2/3 feet. Now you could have worked in feet. You could have taken that 25 inches and called it 25/12 of a foot and worked it out that way. I think that would have been equivalent to 2 1/6 feet working that way, but decided to do the inches for this example today. Let's move on to problem 3. 3 toothpick configurations are shown in the chart below. In question A, we're asked extend the pattern to complete the chart. Well, let's do with our 2 first. Here I see 1, 2, 3, 4, 5, 6, 7 toothpicks and 2 squares. In 3, I see 1, 2, 3 squares. So that squares matches the design number. And I have going across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 toothpicks. Well, not the best artist in the world. Let's see what I can come up with here. We have 1, 2, 2. There's the first square. There's the second one. Third one. And I need to make one more. So 1, 2, 3 more toothpicks being added makes it 13 toothpicks and 4 squares. I just added 3 toothpicks to complete that last square. What about the 5th one? Well, let's draw the first square again. Now the second square. Now the third square. 2, 3, 4th square. To get the 5th square, I'm adding 1, 2, 3 to take me to 16 toothpicks for the 5th square. Sure enough, each design number, each square, since we're using one of the sides, we're adding 3 as we go to each of the next squares. So each square has us adding 3 toothpicks to the design. Now, how many toothpicks will be in the 10th design? Let's follow that logic. We don't have to draw them all, right? We're just adding 3 each time. So the 6th design, which is 6 squares, if I add 3, I get 19. The 7th, square 7, add 3, you get 22. What about the 8th? Well, for the 8th, you're adding 3 to get to 25, and that was 8 squares. The 9th, add 3, you get 28 for 9 squares. And what we're looking for here, the toothpicks, if we add 3 more toothpicks, we're going to get 31 for our 10 squares. So how many toothpicks will be in the 10th design? 31. Now, this is where it gets interesting. Write an expression to represent the number of toothpicks in the nth design. Let's define what n means, all right? N is going to be our design number. Which happens to be the same thing as the number of squares. Now, each time we are adding 3, each design we're adding 3 more toothpicks, which tells us we can start off with just 3n, because we're taking 3 and adding each time. So 3 times n. And you're going, well, why 3 times n? Well, if we look at the first design here, if we were to take 3 times 1, we get 3 toothpicks. In the second design, if we were to take 3 times 2, we'd get 6 toothpicks. But that's a little off, isn't it? It's a little off, because here I have 4 and 7, not 3 and 6. Well, what if I added 1 to both of those? That gets me the 4 and the 7 that were in that table. And so it's looking like I can take then 3n plus 1 is my expression for any design. And if I wanted to test that with that 10th one that we did, we could take 3 times 10 for the 10th design and add 1, and sure enough, 30 plus 1 is equal to that 31 that we found. And so if you're wondering, why do we take 3 times n? That's how we're extending the pattern, but we're adding 3. Yeah, but we're going to represent that by 3 times n. Why did we add 1 to it? Because 3 times the design number didn't get us quite the right number of toothpicks. 3 times 1 was 3. I needed to add 1 to get to 4. 3 times 2 is 6. I need to add 1 to get to 7. And so that is a rule that will work for any designs in this pattern. Now, that was for C. D takes it one step further because, well, why not? Which design will have 175 toothpicks? Well, the number of toothpicks is equal to that 3n plus 1, right? 3 times the design number plus 1 gets me the number of toothpicks. So I can't just put 175 in. That would be the 175th design. What we need to do is to take 175 for the number of toothpicks and set that equal to 3n plus 1. And so for our last two-step equation here of this lesson, let's subtract 1 from both sides to get that n alone. We're left with 174 equals 3n. And the opposite of multiplication is division, just divide by 3 on both sides here. And 174 divided by 3 is 58 equals n. So the 58th design has 175 toothpicks. Now I would go ahead and draw that for us, but I don't think anyone wants to see that at this point. So that is it for this lesson, these 3 examples, these 3 anchor problems for 7th grade, Unit 4, Lesson 6. Good luck.